Hey guys, today we will be going into paired data. So this sounds like a new topic. It's really not in terms of the actual math and the actual process you go through. It's basically the same as a one-mean t-test. It's just that its application is a little bit different. So paired data is the name we use for when data isn't really independent of each other. For example, if you're comparing something between a husband and a wife, or this is actually something I've seen on a college board question, that given 50 plots of land, if we split each plot into organic planting methods and then genetically modified planting methods, you could see that if you have the two types on the same plot, they're likely going to have some effect on each other. So in both of these cases, the data is not independent, and this is when we have paired data. Paired data is when we take pairs of non-independent data and then we compare between that tiny group. So if we're comparing stuff about a husband and a wife, we take a singular married couple and then we compare them, and then we do that for other married couples. For the plots of land, we study each plot of land individually and how they affect each other and the differences between the two non-independent factors. So here I have some practice for how to identify paired data. Out of these 5, some of them are paired data and some of these are not. So looking at the first one, we have a scenario where we are comparing two unrelated M&M factory productions. So you see the word unrelated, and this should immediately set off an alarm bell that this probably isn't paired. So although these factories both produce M&Ms, we have no reason to believe that they're not independent of each other. So you only have paired data when the factory productions have some sort of association with each other. Next, we have twins living together. So first of all, they're twins. If you've taken any psychology course before, you know that twins are already genetically predisposed to be similar to each other, and living together only perpetuates that. So if they're subject to the same environment, then their behaviors and characteristics likely have a very high association with each other. So this is definitely not independent and makes this paired. Next, we have comparing two unrelated schools. Again, you see the word unrelated, so that should tell you that this is not paired. And this has not told you anything about how close these schools are, if these two schools have anything in common that might cause them to have an association with each other. So we have no reason to believe that this is paired data. Next, we have comparing two random neighborhoods. Again, you see the word random, and then if you think about it, we have been told nothing about the proximity of these neighborhoods, nothing that would set us off immediately that these two are paired or have any association with each other. So if these two neighborhoods were along the same street or something, they might have some association with each other. However, there's no one-to-one pairs that we can make here. So no, this is not paired. And finally, we have comparing randomly selected pots of two plants to see their effect on each other. So basically what we have is something like this. What we have is basically a bunch of pots, and each pot has 2 plants in it. And so even though these pots are randomly selected, what we're observing is the stuff within the pots. Our pots of 2 plants is equal to a pair. But because we have clear pairs here, and it has already told us that there is an effect on each other, so we're seeing what the association is between the 2 plants, that would make this paired. What we're doing with paired data is making inferences about the difference between the paired groups. So what is group A minus group B, or something like that? When we do our actual confidence intervals and hypothesis tests, we don't have a defined group A and a defined group B anymore. What we will be working with is a sort of third-party group that is describing the difference between the 2 groups. So like I said earlier, even though the original information that we're given is about these 2 different distinct groups, what we really end up using is the difference between the 2 groups. So like group 1 minus group 2, or in the case of if we're talking about a husband and a wife, so we have a group of husbands and their wives. So what we're going to be doing is we're subtracting the husband characteristic from the wife characteristic, or vice versa. Once we actually start our calculations, there will be no defined husband group and no defined wife group anymore. So it would look something like this. If we have a group A and a group B, so here are our distinct groups, and each of these correspond to each other. So this is one pair, this is one pair, this is one pair. What we're going to be using is neither of these columns. We're going to be using a third-party column with the difference between each pair. For the first row, we would do 10 minus 7 and we would get 3. And doing the same for each of these, we would get our difference column. And this is the final data set that we get all of our important information from. So from our difference column, we can get an x-bar diff. This is the mean difference. So if we averaged up all of these numbers in here, we would get our x-bar diff. That is our sample paired data difference. We could also get our s-diff, so our sample standard deviation of the differences. So again, we would go through this column again and find the standard deviation of this group of data, and that would give us our standard deviation for the sample. So once we get this difference column, this is all we will be using from now on. Our group A and group B are no longer relevant. We just need to know that they exist and that the difference column is derived from these two. However, in terms of calculations, A and B are now irrelevant. All we need is the difference. So the first thing that we can do is a confidence interval on the differences. Again, this should all look very, very familiar because in terms of calculations, this is the exact same as a one sample t-test and one sample t-interval. So this time, the center of our confidence interval is our x-bar diff, so the mean of our differences. And then our margin of error is equal to our t-critical value, that stays the same, and then a standard error. The only difference here is that the s that we use is the standard deviation of the differences, and then our n is no longer really sample size, but more the number of pairs that we have. So if we subtracted 7 pairs from each other, then our n would be 7. And then from there, we can get our degrees of freedom as well. So our degrees of freedom would be the number of pairs minus 1. And that would go into the subscript for our t-critical values. Putting this into practice, I have a question here. So if we randomly choose 50 married couples in a city and record the age of everyone, and when we subtract the wife's age from the husband's age, the mean difference was 4 years with a standard deviation of 2.3 years. We're going to construct a 95% confidence interval for the difference in age between the husbands and their wives. So first, what are our important numbers that we need? We know the formula looks something like this, x-bar diff plus or minus our margin of error, so our t-critical value, and then times our standard error. So the easiest one to find is going to be our x-bar diff. So what is the sample mean in differences that we got? So it says here that we got a mean difference of 4 years, so our x-bar diff is 4. And then it also gives us a standard deviation for the differences. That is our s-diff. So that's 2.3. So now we have the center of our interval, and then even though we have the standard deviation for the differences, we still need to adjust it to create our standard error. So for our standard error, the formula for that is equal to our s-diff over the square root of n. So s-diff is 2.3. What is our n? So that's the number of pairs we have. So how many married couples did we sample? We sampled 50. So that is our n. And our final standard error would be equal to 0.325. So we have our center, we have our standard error. Now all we need is our t-critical value. So for our t-critical, we need the calculator again, and we use the inverse t function, because here we are talking about means. So inverse t, we put in an area, and then we put in our degrees of freedom. Our area is going to be our 95% confidence plus whatever's out here. So that would be 5% divided by 2, 2.5%. And so everything from negative infinity up to this upper wall is 97.5% of the area. And then our degrees of freedom is equal to the number of pairs minus 1. So how many pairs do we have? That's our n, right? So that's 50 minus 1 is 49. And that gives us a t-critical value of 2.009. So we have all the numbers we need now. We can just make our interval. So our x-bar diff is 4 plus or minus 2.00958 times 0.325. That gives us a final interval of 3.346 to 4.654. So what this means is that we are 95% confident that the mean difference in age between married couples in this city is between 3.346 years and 4.654 years. So what if our confidence interval from earlier instead went from -3 to +3? What does this mean? Because our confidence interval includes negative numbers now. Our original scenario was that we subtracted the wife's age from the husband's age, so husband minus wife. And so if husband minus wife is a positive number, that means the husband is older. But if husband minus wife is a negative number, that means that the wife is older. So if our confidence interval is going between a positive and a negative difference in age between the husband and the wife, that means that we can't be really sure in this city whether the majority of husbands are older than their wives or if the majority of wives are older than their husbands. Because in this interval, we have both positive and negative differences. So we can't definitively say whether there's an actual difference between the ages of husbands and their wives in this city. So anytime a confidence interval includes 0, when you're talking about the difference between two means or two proportions, that means that there may not actually be a difference between the two groups. So it's not just in paired data. If you're doing a 2 mean t interval or a 2 prop z interval, because these are both talking about the differences between two samples, right? Our 2 mean t interval is centered around x bar 1 minus x bar 2, and our 2 proportion z interval is centered around p hat 1 minus p hat 2. So this is both talking about differences. And that means that if our confidence interval includes 0 when we're estimating about any kind of difference, that means that the two groups are probably very close to each other and there's no significant difference between the two. So next we'll be going into hypothesis tests on this paired data, so on the differences. So the main question you'll ever really be asked is that, is there a difference between the two data sets? So is the mean difference equal to 0? That's really the only thing that they'll ever ask whenever you're talking about differences, whether it be paired data or 2 mean t tests or 2 prop z tests. They'll just ask, is there a major difference between the two groups? Do we have evidence to believe that group 1 is bigger than group B, etc. So that means that our null hypothesis will always be the same thing. Our original assumption will always just be that the mu difference is equal to 0. So our original assumption will be that there's no difference, and then our alternative hypothesis will most of the time be just that mu difference is not equal to 0, but on the off chance that they do give you a direction, then it would just be either less than or greater than. Please note that I'm using mu instead of x bar now because x bar is solely reserved for samples. When we're talking about mu's, we're making an estimation about the entire population. So here are the steps for our hypothesis test. The first one is, of course, always to list out our POI. What are we interested in the context of the problem? Then we list out our important numbers and our hypotheses and alpha value. And then we do our conditions, which I will go into in a second. They look basically the same. And then we calculate our standard error, our t-score, and then with that t-score, we get a p-value from the calculator, after drawing our t-model, of course. My bad, should have included that. And then we use that p-value to conclude. So, as promised, here are the conditions. They're basically the same, just with different tweaks. So our first one is independence, of course. So the definition of paired data is that one member of the pair is not independent from the other member of the pair. So instead of focusing on that, the independence condition focuses on independence between the pairs. So although the husband and the wife have some association, what we do not want is for married couple number 1 and married couple number 2 to have an association. We want these married couples to be independent of each other. Within the couple, we don't care as much. The definition is that they aren't independent already, so we can just ignore that. So our independence will just be that the differences are independent of each other. Randomization is, again, about the pairs. So we can't just choose a random wife to be with a random husband whenever we do these samples. So what we do is we randomly choose pairs. So these pairs are already stuck together. We can just view them as one entity, but we randomly choose them. Then we have our 10% condition. Did we sample under 10% of all the married couples in the universe? Then we have our nearly normal condition. So if our n is greater than 30, then we can proceed. If our n is between 15 and 30, then we need to draw a histogram to see if it's unimodal and symmetric. And then if it's less than 15, then the parent population must be perfectly normal. So here our n, what is it? It's not really our sample size anymore, it's more the number of pairs that we have, so the number of couples we're looking at. So if it's greater than 30, then we can just chill. We can go ahead. If it's between 15 and 30, this is where it gets a little bit weird, because when you make your histogram, the values that you're using for your histogram are not your group A and your group B. You're making a histogram of the differences. So you would take your differences column and then create a histogram using those values. If it's less than 15, then you just talk about the parent population. So here is our hypothesis test for today. It is the same scenario that we've been using. So we randomly choose, again, 50 married couples in a city, record the age of everyone, and then when we subtracted husband minus wife, the mean difference was 4 years with a standard deviation of 2.3 years. Is there really a difference between the age of the husband and the wife in this city? So what is the first thing that we do? That is our POI. We are interested in seeing if there is truly a difference between the age of the husband and the wife. Next, we state our important numbers and then our hypotheses. So what are our important numbers? That would be our X bar difference, our S difference, and our N and our DF. So our X bar difference is our sample mean difference. Geez, that's a lot. So the mean difference here was 4 years whenever we went around and sampled all these couples. So that is 4. Our S difference is the standard deviation of that 4. So that is 2.3 years. And then our N is the number of couples that we're looking at, so 50. Our degrees of freedom is our number of couples minus 1, so 49. And that's actually all of our important numbers. Note here that I was actually able to get a degrees of freedom because the math that we're using here is the same as that of a one sample t-test. You only need to use your calculator to get your degrees of freedom ahead of time when you have 2 samples for means. Next, we have our null hypothesis. So what is our original assumption about the mean difference for all the couples in the city? Our original assumption will be that there is no difference. Then our alternative hypothesis will be that it is not equal to 0 and yes, there is a difference. So there wasn't a direction specified in here. If there was a direction specified, it would be something like, is there evidence to believe that husbands are generally older than their wives or wives are generally older than their husbands? That would be giving us a direction to go into. But because they didn't say either one is older than the other, then we just say not equal to. And then our alpha value is equal to 0.05 as usual. So we can go into our conditions now. First, we immediately see the word randomly here. That's good for us. That tells us that we can just combine our independence and randomization because since the couples were randomly chosen, they definitely don't have any association with each other. Because the sample was randomly selected, the age difference in one couple should not affect the age difference of another. Note that here I'm only referencing the difference. So we're talking about independence between the differences of the pairs, not if there's independence within the pair. So it's not that the age of one husband should not affect the age of another. It's does the age difference in one couple affect the age difference in another couple. Next we have, since we got our randomization condition out of the way as well, then we have our 10% condition. In your average big city, there are way more than 500 couples. So we can say that 50 couples is probably less than 10% of all couples in the city. And finally, we have our large enough condition. So we got lucky. Our n is greater than 30. So because it's greater than 30, we're good to go. So because the number of pairs, which is 50, is greater than 30, the sample is large enough. Now we can conclude and tell the people what we are about to do. Because the conditions are satisfied, we can proceed with a one sample paired t-test. So our one sample t-test is still here. Again, we only have one sample, and then because we're working with means, it's a t hypothesis test. But we also need to throw in that it's paired, so you just put in the word paired. So one sample paired t-test. So next we need to get our standard error in order to get our t-score. So our standard error of the differences, x bar diff, is equal to our s diff over the square root of n. So our SDiff is pretty straightforward. It's up here, 2.3, and then our N is 50. So that would make our standard error 0.325. With that standard error, we can now get our t-score. So t sub df, so with the subscript of 49, is equal to our x bar diff minus our mu over the standard error of x bar diff. Our x bar diff we already know is 4, and then we assumed our mu to be 0, so minus 0 over our standard error of 0.325. That is equal to 12.298. So that is our t-score, and with this t-score we draw our t-model and flag our t-score. Oh geez. 0, you know what? 5, 10. There is our t-score of 12.298. And then we go from there to the nearest extreme. So this area right here is what we're interested in finding. So putting that into calculator language, the probability that our T49 is greater than 12.298 is equal to, and then we put in our calculator language. So TCDF, because we're working with a t-model, and then we put in lower bound, this should be getting really familiar, upper bound, and then degrees of freedom. So our lower bound, looking at our model, would be our z-score of 298. Our upper bound is infinity, and our degrees of freedom is 49. But we're forgetting something. We forgot to consult our alternative hypothesis before doing this whole calculation. So looking up here, we note that it says not equal to. What do we do when it says not equal to? Well, because no direction is specified, that means we need to look in both directions. So we need to multiply by 2. So our TCDF times 2, and that would be equal to 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 6, 8, 3. That's our p-value. You already know we're going to reject the null, but we still got to conclude. So our conclusion is going to look like this. So, if there was truly no difference between the ages of husbands and their wives, the probability of the observed data occurring would be very long number. Because the p-value is so small, very long number is greater than alpha, which is equal to 0.5, I reject the null. So this should all be looking really familiar. It's just that you can see that the application is different. This is basically the same as a one sample t-test, so I hope that this was just a bit of a refresher for you. But that's it for today. That is paired data for you. That is all of paired data for you, actually. Next video, we will be going into the chi-square distribution. So I'll see you there. Thanks for watching. Hope you learned something. Peace.